Right then, next up, you've all met David before, I imagine. So this is David Holland from Salix, and he's going to introduce some of the techniques they're using for bank stabilisation.
Hi, good morning everybody. Yeah, really I'm just going to fly through a load of slides, really of how Salix approaches bank erosion issues in the UK, and some of the techniques and materials and solutions that can be used to manage soil erosion, riverbank erosion. Start by saying that bank erosion is a natural process. In many rivers it's a key driver to many niche habitats and to sort of flood management. So erosion is not a bad thing. All the examples, and when we're talking of erosion here, we're looking at erosion that's either accelerated by human impact or erosion that is threatening an asset. So we do a lot of work with Environment Agency, with pipeline people like Wales West Utilities and National Grid, who often turn up and find a gas pipe sticking out of the riverbank after a major flood. So a lot of this is driven by the need to actually take action. Often you don't need to if it's a rural area and it's a natural process. Just to reflect on, really started off from land drainage in the 50s and 60s. Hard engineering has been used an awful lot in the UK. It's something that I think Chris Bowles touched upon yesterday from CBEC. Generally it's not very good, but it still goes on a lot. As Volker was saying, in Germany you have, if you use hard engineering on riverbanks, you cut off any interaction between species that live in the water and need to come out onto land as part of their life cycle. With soft bioengineering, or as Chris called it yesterday in America, biotechnical engineering, the environment actually typically call it soft engineering. We'll call it bioengineering. You don't get those issues. And we see an awful lot of it, and the impact is very obvious. Typically where you get hard engineering, extensive hard engineering, downstream you always have instability, and that's a classic. There's a scheme on the River Tui in Carmarthen where the council every year do 100 metres of blockstone, and they're just chasing the river downstream year after year after year. Sooner or later they'll realise they have to stop and actually do something different. Again, yesterday it was touched upon, but everything about hard engineering is bad. When I first started doing bioengineering 17 years ago, it was very much hard engineering, and we had to convince engineers that this could potentially be an alternative. Now I think it's becoming more of a last resort, not a first thought. I think people are realising that soft engineering is credible, bioengineering is credible. You can see impact of hard engineering. This was originally installed to protect the gas pipeline, 4 metres high gabions. You can see downstream of the gabions a huge blowout, a 4 metre pool that had cut into the bed directly downstream. CBEC did some modelling for us. So this is the hard engineering on this outer bend, and you can just see the hotspot of energy that is then released when it comes off the hard engineering on the downstream end, creating this huge blowout and actually exposing a high pressure gas pipeline in the bed of the channel. See that real hotspot where the gabions terminate. So on this particular scheme we've gone in and de-engineered it. We've actually taken out all the gabions, graded the bank, used softer bioengineering techniques, and that hotspot has now disappeared on the modelling. It's gone. That big pool is naturally filling in with river gravels coming downstream. So very much the whole thing is to work with natural processes. Unfortunately, schemes still do happen. Colleague Richard, we were dismayed at the scheme. It was a river diversion, 600 metres last year. Was it an over-eager engineer? No, it was a biodiversity officer from the Environment Agency who insisted that this went in on a lowland river. It's absolutely scandalous, and we've kicked up a huge stink, and we don't do a lot of work in the Midlands region at the moment, but we're sticking to our guns. So bioengineering effectively is a term that we use for soft engineering. It's the use of vegetation. Normally it's used with either man-made or preferably where possible biodegradable natural fibre products. Of course, blockstone and riprap has been used as an engineering tool, but also vegetation has an engineering function. And the three main ways vegetation works is that roots physically bind soil particles together. They transfer the strength of the root into the shear strength of the soil. They also, and this is what people think of, the roots reinforce the soil as most important. It is important factor, but not as much as this armouring. The shoots actually bend over, protect the soil surface, and equally as important is the fact that vegetation is rough and it actually slows down velocity locally, and that takes a lot of energy out of a flow. So vegetation is nature's way of holding banks up and working with natural processes with a minimal impact downstream. There's also a small geotechnical benefit to vegetation. Vegetation basically lets less water go into the banks, so the banks are drier, but it also then physically holds up banks with the roots in this buttressing effect. Again, when we first started over the years, we've had to battle hard to convince the engineering fraternity that this is a genuine engineering solution. People think that there's no data available. We know that there is. Certainly we've done a lot of work very hard to sort of model rivers that we've done, and we know sort of flow velocity, shear stresses, stream power that bioengineering has withstood over sort of projects that are 15 years old. We know also in alpine areas they've done a lot of work. This is a large flume created by the University of Vienna down in the Alps, where they're looking at different willow bioengineering techniques, and they send controlled discharges from the reservoir over it, and they can measure a scour, damage to vegetation, soil loss, and you can get a good idea of what sort of flow velocities these systems can take. In America they've done a lot of work on grass species, particularly with reinforcing grasses with different geotextiles. So we know, particularly with grasses, really accurately what flow velocities they can withstand and for what durations. So how do we use all that? The first thing to do is to look at the erosion process, because you can't go designing a revetment, and a lot of revetments are designed without really considering what the processes that are likely to go on or that are currently going on. So here's just two examples. This is a classic sort of gravel bed river. You've got a sort of undercutting of the toe, that steepens the bank, and the bank collapses in. It's a classic turf collapsing in from this cantilever failure. Here you've got a tree, an impingement of flow, creating scour at the toe. So here, a really simple technique that we use quite a lot is we've actually taken the tree out. You can see on the left, the stump is gone. We've used that whole tree, cut into big branches and brash, and used it below bed in a 1 metre pool. A metre wide revetment effectively we've created, and that just creates this roughness that we're looking for. And then we're not worried about the bank above. The footpath that we're protecting is probably safe. So over time we just let that bank naturally grade itself out. So we've taken away the problem of the tree and we've reused it. About 30 metres of bank erosion solved in about one afternoon, literally. So bioengineering can be really, really simple. Here the asset is a footpath, it's a low value asset, but still it had to have some sort of work to protect it. The original idea was to go 4 metres high with blockstone. So just really a value engineering alternative. Different erosion process is very much associated with rapid drawdown from rivers, often in very fine silty soils with low cohesion. We were lucky enough to work on a project where, on the River Team 2 years ago, that hadn't come out of bank for 50 years, since 1954. And the year we worked on it, it came out of bank, came up 6 metres out of bank 4 times. So we had good first-hand experience of this drawdown process. How do I get that going? Help.
Hand over the top, left-hand screen. Okay.
Lily, you're the technical genius.
Why is it not working? David, what have you done?
Broken it.
David's broken it.
I'll show you after,
Just,
if
yeah.
anyone's interested. And it's
Just
nice,
like
it's a time lapse of a flood and shows the bank.
I'm just going to do it like this.
Alright, the old fashioned way.
The old-fashioned way. If the links fail, we'll make it work this way.
So effectively there's our diggers, and this is a gas pipeline scheme.
Coming up.
Yeah.
No, we can see it. It looks great, by the way. The water's rising. Quite muddy.
If anyone's interested, I'll show you after, because it's a nice little clip.
See.
How do I get that now? Does this count for my 15 minutes, or can I go over?
No, don't mind.
It starts again though, the clock's reset.
Preset, excellent. Okay,
No.
I forget that. But again, in that situation, this is a major gas pipeline that takes all of Hereford and Worcester's gas. There's a really significant asset that had to be protected. The toe, there was scour at the toe, but the main process here was just these really weak soils collapsing in. And the only solution really was some quite major engineering to basically dig out the whole bank because it was so saturated and just constantly slumping. Grade it back to a natural angle of repose with imported material where needed, and then bioengineering on the top. But here there's quite a major erosion problem. It ends up being £1 million project to protect the gas pipeline. But again, what we've eventually come up with is now a more natural channel. It's soft lined, it's not hard. And really important again to consider the vegetation zones. As pointed on yesterday, I think Chris in his talk, the toughest area to design for bioengineering, for soft engineering, is the toe and the margin. The toe because you can't get anything to live down there if it's below water. You can't use a bioengineering. So you need to possibly, if it's deep water, have some bit of stone or a large wood or something in there. And the other tricky area is this marginal area where you get constant fluctuations of water. So you're constantly getting fluctuation. If you ever tried seeding a riverbank, you often end up with a bare 1 or 2 metre patch at the bottom where the water's constantly coming up and down, and the seed and vegetation just can't establish. Which is why really, a lot of you saw yesterday, and those of you who come today can see these products. This is why these were invented, and why they're so much used on river projects now. It is because they are mature marginal plants that are adapted to that little flood area, that first sort of toe of the bank. And we found over the years the only way to get them to work as a guaranteed thing is to grow them to a really high state of maturity, so grow them for 12 months off-site in a nursery. If you put young plants in them and send them out 6-8 weeks old, they'll just wash out or get flooded out, they'll drown, or drought will get them if it's dry. So that we found the only way to really work is to have them mature. Another sort of regular soft engineering technique that's used, and Volker mentioned it in his speech, is brushwood faggots. Very versatile, but the only time we would really recommend using them is where they're completely submerged and there's no chance of them ever being exposed to the air. When they're underwater and anaerobic, they almost fossilise and go hard. The moment they're exposed to air on a regular basis, within 2 years they're fragile and broken down. But they're very good for lifting up the living part of a bioengineering solution. So here in relatively deep water, this is an alternative to sheet piling on a rail, 2 kilometres of railway embankment. We're just using the brushwood as general fill here, and to raise up the living element. So the coir pallet and the coir roll can actually survive. If they're straight in there, they'd be too deep. So this is a project for network rail. So it's direct alternative to sheet piling for 2 kilometres. You end up with just within the first 12 months, a really nice, dense, 1.2 metre wide margin, absorbing all the flow and wave action. And obviously very, very good habitat. Another very natural way, this is a project for Natural Resources Wales, where they took out a weir. The channel responded by the bed dropping, a lot of gravel flushed through, and extensive bank erosion. It's a salmon river. They were losing up to 1.5 metres of bank a year, huge sand and silt inputs into the river system. So this was more, not protecting an asset, this was more really just stopping the release of fine sediments into the river. Really, really simple again. I think this is about a 2-week job. Just graded the bank. You can see on the opposite side there's a load of willow trees. So we've graded the bank, just put some biodegradable coir matting, a blanket, we find a coir blanket with a coir net over the top works really well in quite high energy situations. At the toe, we've just cut branches from the other side, from the willows. We've just laced them along the toe of the bank. Again, one where grass won't grow, but also to add this roughness and to get sediment to deposit out. And that's it after about 6 months. And that's the willow at the toe. So you can see there's a lot of roughness there, you get a lot of slow inner flow and a lot of sediment dropping out. So a very, very natural way of managing erosion rather than, it's not a total fix, but we're managing the rate of erosion and getting vegetation back on there. Again, you can see the coarseness of the coir fibre is very good at trapping the fine sediment, and now you get things like canary grass, phalaris coming in, colonising in those areas. These sort of mattings and geotextiles and grass, work in quite high energy situations, or can work, but vegetation always has a limit. There's always a cut-off where vegetation won't work. You can see here relatively well-established banks, one big flood, very significant bank erosion because the grass has failed. So we work a lot with these three-dimensional products. They do allow really vegetation to be used a lot on dam spillways, a lot on flood defence embankments, where only blockstone or concrete blocks would be used. They basically double or even triple the flows that vegetation can withstand. This is a direct alternative to blockstone all the way up the bank for a network rail. And one example we always throw in, because it's the first high energy river to be done really with bioengineering techniques 10, 11 years ago, started in 2004. It's the River Ebu in South Wales. Rock roll tow, willow and faggot to get something to grow, and then these three-dimensional turf reinforcement mats. This channel was 1.2 kilometres of new housing development all the way along, all colliery shale, and the original proposal that went through land drainage consent was 2-ton blockstone set into concrete all the way through, and it was only a presentation like this where the client's engineer sort of heard us saying we could do this sort of thing, that they said, oh, okay, how much does it cost? It was half the cost, so we got the contract on our design and build with our sort of warranty in place. And it's the first scheme, and I know Natural Resources Wales Environment actually use this site a lot to show people what can be used instead of blockstone. So around some headwalls they had the original blockstone still went in as tie-in, but you can see the soft engineering 1 year and 7 years later, an awful lot better than blockstone would have been in that environment. In fact, the blockstone is now failing. There's blockstone in the middle of the channel, and the soft engineering has functioned perfectly. Blockstone's big, flows get in around it, and they can actually move it far easier than they can destroy the vegetation. Again, we mentioned it yesterday, so very quickly, again, vegetation, constant wave action, constant flow in this marginal area. We found something as simple as adding a rock roll, and potentially in the future these schlicht rolls, in front of coir rolls, in front of the living element, can actually give that bit of protection. So here on this same reservoir, coir rolls have completely failed, the wave action is too great. But simply by putting a rock roll in front that absorbs the energy rather than reflects it, you can get vegetation to establish in areas where it wouldn't naturally grow. And now it's established, it's a long-term solution. You see on the River Taff by the Millennium Stadium in Cardiff, you can almost see that rock roll sucking in the wave. Not much is reflected and refracted, there's a bit of splash, but most of it's just getting slowly absorbed into the small stones. Again, the rock rolls we did yesterday a lot with C.WEMs and Ruth, but what we're finding now is it's the building blocks of bioengineering in higher energy situations. You can see it's a gravel bed river, it's very mobile. You struggle to get bioengineering to work here without a rock roll tow, but it does then allow the rest of the project to be soft engineering, and we saw from Ruth's presentation yesterday you actually get very good invertebrate habitat in the rock rolls. How am I for time? So yeah, again, just yesterday, just reiterating that they do fill up with fine sediment. They have the coarse sediment in them already, fill up with the finer sediment, so they match natural river gravels, and then they will vegetate. I'm just going to show a few last slides. Again, Hamish and Chris talked a lot about large woody debris yesterday, and it's something that we're seeing a lot more of. So this was a gas pipeline, again taking most of the gas into mid-Wales, just off the River Severn, a little river called the River Rhew, and they had a bit of a shock when the aeroplane the helicopter did the 2-weekly flyover and saw this pipe hanging out of the bank. The bank had retreated at 8 metres in one flood event. Incredibly mobile system. So the gas pipe was actually exposed in here, but the bank was moving at about 8 metres a year back into the pipeline, which actually runs directly into it. So we ended up doing work on the whole river. It's an incredibly mobile system, and we involved CBEC, and we came up with this plan to basically put a lot of wood in the channel. So again, we use these root wads. See the eroding bank. There's a lot of root wads on the banks to slow flow locally, to add roughness. And again, you can see there's a rock roll tow in there. And on the upper banks, we used a lot of brush mattressing, that's a willow technique. You lay willow branches down, cover it in soil, and they all root. Combined with the fact that these trees are actually willows as well, harvested from the local catchment. So because they're willow, once they're installed, they actually start to live again. So you get the roots sending up and the trunk sending up new growth. So you end up with a living mass of willow on that bank. Same photo. We also put some large woody debris in. Because the gravels move around so much in flood, it's quite difficult to stop things undercutting and to stop major sort of river realignment. So we added woody debris that was actually contributing to the problem. It was causing gravel to deposit, to deflect at the pipe. So we took out the wood and replaced it. And this is quite amazing to see the response that one tree effectively can cause in a mobile river system. That's installed. That's the location of the woody debris that we installed. And after one flood event, that's the response. So that's the large piece of wood. The exposed gas pipeline runs here. So now we've basically built up a huge gravel shoal in front of the pipeline, so there's no way that can get undercut. You notice we've actually gone quite hard over the gas pipe. There is some blocks in there because the client wasn't prepared to take any chances with that exposure happening again. So you can see the bedler response is really dramatic, and that stayed there on several major bankful flood events. And finally, a lot of people ask, and I've already put this last one in, just to show, well, how do you know that these things will last long term? The first time these root wads and wood were used as a revetment was a demonstration project for then Environment Agency Wales on the River Dewlice, and the whole idea was to show landowners and people within the agency that you didn't have to use blockstone on Welsh rivers, because that's all they use is blockstone everywhere. So here we're using bank grading, a root wad toe, and then just live cuttings and a geotextile on the bank. We installed, I think, about 15 of these large trees. You can see the idea that you key them back into the bank. Most of the anchorage comes from being keyed into the bank. And there they are installed. And the idea is that one picks up the flow and deflects it onto the next one, and so forth. So when the flow's coming, it's like a deflection technique, moving the flows out away from the bank edge. So see, that's the channel. I think it was 7 years on. And that's that same bank now. And you notice that there's not just willow, there's other things come in, there's grasses come in, there's gravel, it's now stable. The whole reach is deeper and better for fish passage. Finally, that is one of those root wads. Again, they were willow, so they've actually, the original root plate has actually grown in every direction. So you can imagine the fish cover and habitat that provides underneath is fantastic. That's it in the winter and that's it in the summer. So again, you can imagine the structure of that on a riverbank is incredible habitat as well as providing long-term stability. Thank you.